Hello guys, welcome in this new video. In this video we will be talking about quicksort and iterative quicksort, and we will also discuss somewhat about like the comparison between merge sort and quicksort. So if you haven't watched the merge sort video which was uploaded before this one, so do check it out and let's get started. So basically quicksort is another sorting algorithm which is actually preferred to sort array elements that are bigger in size, and merge sort, as we talked about in the last video, is actually used to sort, and like it's actually preferred to sort the linked lists. And quicksort is just another algorithm which actually uses a pivot element, where we have to actually choose a pivot in an array and then partition the algorithm and sort them according to this algorithm, quicksort algorithm. So first of all, I want to say that there can be four possibilities to select a pivot. Either choose the first one, the last one, or randomly choose any element as a pivot, or choose a median as a pivot. But uh, actually there is a great disadvantage in using the first two, because let's say the first or the last element that has been picked as the pivot is either the smallest or the largest in the array, and we and the given array is already sorted in either ascending or descending order, so the number of comparisons get the maximum in these cases. So the better thing is that either pick the element pick the pivot element randomly, or pick the median as the pivot, or if the array size is smaller, then use the insertion sort. We will talk about insertion sort in later video, but these these are the cases where we can actually optimize this algorithm. Okay, so before getting ahead, let's take a look on how quicksort works. So the pseudocode is given here. Basically, we will just check if low is less than high. These two are the pointers pointing to the partition, where the low is the starting index and high is the ending index, and we will just partition the array and apply quicksort on both the halves. So better to give you a better understanding, let's first visualize it. Before that, just see on this image that here they have actually selected 70 as the last element, and they have partitioned around the pivot, and then they get these two areas. Then again they select 40 and partition around these two, so 10, 30, and an element sublist and an empty sublist or array, and then around 30, so they'll get 10. Similarly, getting it in the right part as well, 1980, so they get the partitions like this. But I think this will not visualize you, like this will not give a good impact on learning this thing. So let's see this implementation, where we can see that there are 8 elements in an array, and it actually picks the pivot element randomly. Okay, so the I'll just give you a small quick walk through this algorithm here, so that you can understand it easily. So let's say the pivot is selected as the third indexed element, that is 438. Now in the next step, we move the pivot to the end, okay, and swap, that is we swap the last indexed array with the pivot index element. Now we actually partition the array, so we will do the partitioning of the subarray. Then we have these two markers, so these will be pointing variables. One you can call is as low, or and this one as high, or you can also call it as left, or this one right. And we we first check, we move first this left pointer to the right until it reaches a value greater than or equal to the pivot. So the element which is greater than 438 or equal to that will, it will go up to that. So it goes up to 730 and will stop. Okay, now it will, what it will do is, we will now the right will move the right pointer to the left until it finds a value less than or equal to the, sorry, only less than pivot, not equal to, because the equal to case is considered here. So it is, we got an element that is less than the pivot. So we will now swap these two elements. Now again we will move the left bound to the right until we reach an element that is greater than or equal to 438. So we got a point. Okay, we will wait now, and we will now move the right pointer to the left until we get an element greater than 430, sorry, less than 438. So we will go up to 671, then again to 188, and now we will stop because we got an element that is less than 438. So now we have these two fixed and we will swap them. Now again we will apply that moving of the pointers, and we will step right and again right. So we stop because we got an element greater than 438. Then again we will move the right bound, but it has got the element but the bounds are crossed, because the left pointer should always be less than or equal to right pointer, but it is not the case. So what we will do is, as the bounds have crossed, so all the elements less than the greater uh, left bound will be less than the pivot, and all the elements right uh, right to the left bound are actually greater than the pivot element in the sub array. Okay, so we will swap the pivot and the uh, left bound dead indexed value element. So we will again now call the quicksort in this left sublist, and after that, when it is done, we will call the right sublist. So now our focus is on 0 to 3. So select pivot randomly selected, then again, or you can also select the pivot as the middle element of the array as well, but it's up to you. But I told what are the disadvantages of taking the pivot as the either the first index or the last index. Okay, so this way it goes around, then we check until the bounds have crossed, then we again call, after fixing this we again call in the left sub list, then select a pivot, again get it to the last index, and then check for the right and left pointers, and get the elements accordingly. And by doing this we actually will be getting sorted elements. So I'm just fast forwarding this one, so that I don't want to take much of your time. I will actually give this link in the description, so you can also test it accordingly. So then here, now after doing this, we came to this right sub list. So we have called the quicksort function here as well. So this is being done. So at last we will be getting a sorted array. Okay, so you can see here there are other visualizations also which you can see, which actually uses horse partition and lomuto partition as well, with using javascript in the web browser. So you can see this as well. I will link them in the description. And so this was actually the visualization. So I think you got to understand how the quicksort works, and you can see this code as well. But let's somewhat analyze this quicksort. In the above case, this can be the recurrence relation given here, and also the this can be actually done in a recursive way as well as iterative way. So in this article they have given the recursive way. I will also discuss about somewhat about the iterative quicksort. So first let's analyze it. So in the worst case, if you analyze using the this recurrence relation, so you will get that in the worst case order of n square is the worst case time complexity for this quicksort, and for the best case it will be n log n. Sorry, average case it will be n log n as well, and also for the best case as well. See here it is given. So you can analyze it like this, like either using the master's theorem or by going like putting n equals to 1 starting from base, then 2, then going up to n, and then adding them like that as well. So is quicksort stable? The default implementation which uses the last index is not stable. Okay, and however any sorting algorithm can be made stable by considering indexes as comparison parameters. Is quicksort in place? Yes, it is in place sort algorithm because it doesn't need an extra array to actually sort these. That was the case in merge sort which we discussed earlier, which where we have to use an extra temporary linked list. Okay, and this quicksort will actually not work when there are duplicate elements. So in this case we have to use three-way quicksort where we divide our partition like this: the elements less than the pivot, the elements equal to the pivot, and the elements greater than the pivot. You can see this implementation as well, the three-way quicksort, which actually uses Dutch. It is similar to Dutch national flag method, but it is somewhat advanced version of it. But yeah, you if you want you can see this one as well, but I will be not covering this one. And yeah, and also why merge sort is not preferred for sorting arrays, because quick sort is an in-place sort. Okay, and merge sort is not. Also the allocating and deallocating of extra space used for merge sort increases the running time of the algorithm. Okay, but in this one we can get order of one getting time, like fetching time for an element, so it is not a good thing. And quicksort is also a cache friendly sorting algorithm. It is, as it has good locality of reference when used for arrays, and also it is tail recursive, therefore call optimization is done. And why is merge sort preferred over quick sort for linked list? It has been discussed by me in the previous video. Also, just for a recap, that merge in the linked list we cannot have order of one time fetching for an element because they are not sequential array like arrays. So this was it. And how to optimize quicksort, that it takes order of log n extra space in worst case. You can see this quicksort tail call optimization method as well. So these are some snapshots, and just let's somewhat quickly look at the iterative approach. So this one is this algorithm is a recursive algorithm, and these are actually, and these can be the methods to actually optimize these. I have already discussed them in the starting, and this one is the iterative approach. So the algorithm is same, just the implementation is that we do not we are not calling recursively, and just calling the function and doing iterating over and over again. Okay, so this was it. Also this can be optimized as well, you can read here as well. So this was it, and I will link down all these links in the description so you can check them out as well. So thank you for this video, and keep watching and keep learning.